Okay, question number 33. I actually really like this one. It's a little bit, I guess, could be challenging conceptually. So let's go ahead and get started. So you have a spherical tank of radius 5 meters contains water that's slowly draining out. At the instant that measurements are taken, the maximum depth of the water in the tank is 2 meters, and the depth is decreasing by 1/3 meters per second. What is the rate of decrease of the volume of water in cubic meters per second at that instant? So what I want to do here is basically I want to figure out what does this look like. So I mean, basically it's like a spherical tank, right? It's kind of hard to draw a sphere, but essentially it has this like water level and it's decreasing. So if we look at this in 2 dimensions, essentially what we have is a circle that, you know, the how do I say this? It's basically like not a semicircle, like it's not like a half circle, but basically it's like it would look like you have this circle and then you get this kind of weird half circle-ish type shape. I'm not really sure what the word is, but anyway, that's what it would look like. So what we can do is we can model this in 2 dimensions, and then we can use calculus to figure out the volume, in 3 dimensions. So first thing that I want to do here is go ahead and define my variables. So, if this is x and this is y, then this is going to be my radius. So the radius of the entire circle is going to be r. I'm going to call it capital R. And then the height, well, let's go ahead and write out, what this would look like using the circle equation. So I would have x squared, and it's centered at x equals 0, so that's perfectly fine. Plus, and then look how we shift the circle up by its radius. So it's no longer just y squared; it's actually going to be y minus r, and then all that's going to be squared, and then of course that's going to be equal to the radius squared. Now the key here is I want to define my variables in a way that's like meaningful to me. So I'm just going to say that for any change in y that we have, I'm going to say that that is going to be equal to lowercase h. And then similarly for any change in x that I have, I'm going to call that r. So lowercase radius, and which is basically just going to show how the initial radius changes with time. So I can go ahead and rewrite my variables. So I will have replace x with r. So we're going to have r squared, and then I'm going to replace y with h. So plus h minus r squared, and then that's going to equal r squared. So I'll go on ahead and subtract this from both sides. So minus h minus r squared. And I will be left with, let's see here, r squared equals, capital R squared minus h minus r squared. And then I can just simply take the square root of both sides. So now I have r equals r squared, square root of r squared minus h minus r. All that is squared, of course, and then take the square root, right? Okay, so let me go ahead and erase all this, create some more space. And now the key here is I want to figure out what is the volume at any given height. So essentially, and the other key here is that because water is draining down, that means that the height is actually a function of time, right? So essentially the way I would write that is I would just say, all right, what is the volume as a function of the height, which is a function of time? And the way that I would calculate volume is by using calculus. So I would just, essentially figure out what is the area. And again, my limits are going to be 0 from the height as a function of time. For my radius squared, and then of course, this is just going to be pi r squared, right? Because I want to get the area and then kind of revolve it. So I'm going to need to put my pi here. So pi r squared, and then using this integral, pi r squared d, actually, what am I missing here? Yeah, and then this is going to be with respect to height. Okay, So now I'm just going to plug in this for r, and I'll just drop the square root since we're squaring it. So I will have that v as a function of height, which is a function of time, is going to be pi multiplied by the integral from 0 to h of t for r squared minus h minus r squared, and then of course all of that is going to be with respect to h of t. Okay, all right, so now what I want to do is I want to figure out, all right, they tell us that at the instant when the tank is 2 meters, or when the water in the tank is 2 meters, so I want the height at 2 meters. So let's see here. What I want to do is I want what is dv2 dt. So essentially what I'm going to have to do here is I will have to I'm going to have to take the derivative of this right here. So whenever I'll just show it symbolically, that way we kind of see what we're getting at here. So r squared minus h minus r squared dh of t. All right, so whenever I do this, I need to figure out what does that equal. Now, if I take the derivative, right, with respect to time for this integral, then I'm going to have to use that fundamental theorem of calculus. So I will end up having, let's see here, I'm going to end up with pi times r squared. And again, the key here is that I'm going to plug in 2 for h of t. So I will get r squared minus h, minus r. Let's see here, squared. Whoops. And let me just go ahead and erase this so I have some more room. So I'm going to have all of this, and then it is going to be evaluated from 0 to 2. And again, it's just good. The antiderivative is just the initial function because I took the derivative of the integral, right? Now, the other thing that I need is, again, because h is a function of time, then I am also going to need the derivative of the height with respect to time. So this is going to be multiplied by the derivative of the height with respect to time here. Okay, so now I'm just going to clear some more space. And I probably should have added an extra slide, but I think it's okay for now. I'm just going to erase really quickly. Okay. All right, so now what I'm going to do is let's just go ahead and evaluate what is this equal to right here. And sorry, this pi should be multiplied by everything here. Let's just look at this lower limit. So 0, if I plug in 0 for the height, and then I square that negative r, I'm going to get a positive r. So I'm going to get r squared minus r squared, which is just going to go to 0. So I'm just going to ignore that for now. And I'll stick with my upper limit here. So let me go ahead and go back to what I was doing here. So let's see, t. So this is going to be equal to pi times r squared minus 2 minus r squared. And again, this is, whole thing multiplied. And then this entire thing has to be multiplied by dh dt, which thankfully they tell us here. Look, it says it's decreasing 1/3 meters per second. Okay, so this is just going to be 1/3. So thankfully now I know that r is just the constant, right? That's just what they, what the radius was, what we defined. So in this case, it's going to be 5, and now let's just plug and shove. Sorry about that. So whenever I plug in all those values, I will have pi times 25 minus 2 minus 25 squared, and then multiplied by 1/3. So whenever I run this through, I'm going to get Let's see. I feel like I did something wrong here because 23. Hmm. Oh, yeah. Sorry. I did something. Sorry, this needs to be a 5. Scared me for a second. So let's see. 3 squared is 9, so 25 minus 9, then 1/3. So I'm going to have, all right, I'm going to have 16 pi divided by 3. And that is going to be my final answer. And of course, this is the rate of change of the volume whenever the height is equal to 2. So the correct answer is going to be A. Okay, sorry, that took kind of a while to run through, but hopefully it makes sense. If you have any questions, feel free to comment below, and I'll see you guys in the next video.